welcome back to my YouTube channel. So we are going to be looking at how to solve partial differential equation using Fourier transform. So in our last video on Fourier transform, we outlined that the formula for Fourier transform for cosine, the Fourier cosine transform for a function of t is denoted as this, and for sine transform is denoted as this. So now I gave you the general formula for the function of t, which is your inverse Fourier transform. So, but in this case now, this function of t, this is the inverse Fourier transform for your cosine formula, and this is the inverse Fourier transform for your sine formula. So now we're going to be expressing it as x, because the variable x is what is mostly common in our problems. So now we have two types of Fourier transforms. We have two types of Fourier transform. We have finite Fourier transform and we have infinite Fourier transform. So the one before us here is the infinite Fourier transform, because limits goes from 0 to infinity. It does not end. Then your finite Fourier transform are the ones that the ranges are between two definite figures or two definite numbers, just like from 0 to 2, or from 0 to 5, 0 to 10, or 0 to L. So we denote it as L for a definite figure. So that's that. So now let's express the variable as a function of x. So the Fourier transform for a function of t can be noted as fx. That's the Fourier sine transform, fx of n, square root of 2 over pi integral from 0 to infinity of ft sine nx dx. So now we're going to be making use of finite Fourier transform, meaning that our limit will go from 0 to a definite figure. So this is the finite Fourier sine transform of a particular function of x. Or let's use n. Since we're using n, let's use n. Let's use n to denote let's use n in place of omega. So this is square root of 2 over pi. It's calculated from 0 to L. This is a finite sine Fourier transform. Then function of x, let's use x in place of t. Let's use x here in place of t, and we use n in place of omega. So function of x sine nx dx. So we are going to be making use of this finite Fourier sine transform to solve PDEs, and this also applies for your cosine transform. This cosine transform can be written as 2 over pi, square root of 2 over pi integral from 0 to L of function of x cos nx dx. So now, my function of t, or function of x, my function of x is the inverse of this and the inverse of this. So, but for sine, function of x is denoted as square root of 2 over pi is going to come from 0 to L, function of sine function of n sine nx dx. Right? And function of x for cos, for your cosine sine transform, can be denoted as square root of 2 over pi is going to come from 0 to L, function of n c cos nx dx. So now there's a way we can shorten the formula for your Fourier sine transform, your finite Fourier sine transform. There's a way we can shorten this formula and shorten this formula. So now, since fx, which is your inverse of this, is denoted as this, and remember, I can find this f subscript n of n in this, right? So I can multiply these two. I can multiply this by this. Now when I substitute this will multiply this, right? So I can write Fourier sine transform of n to be integral from 0 to L of fx sine nx. Now, because I assume I substituted this to this, right? So I assume that this will multiply this. So when this multiply this, my new fx will be equal to 2 over pi integral from 0 to L function of x sine nx dx. So this is the formula we're making use of while solving PDEs. So the same also applies for Fourier cosine transform. Then my f subscript c of n will now be equal to integral from 0 to L of function of x cos nx dx. Because this is a more simpler formula to remember. So this is function of x of c. This is for cos integral comes from 0 to L, a function of x cos nx dx. So now this is what we call inversion formula. So the inversion formula is what we use to round up our solution to PDE. So the inversion formula for x, inversion formula. So now, so like I said, we make use of this and this to solve PDEs or partial differential equation. So the inversion formula for your Fourier sine transform, remember this is your Fourier sine transform, and because of the limit goes from 0 to L, which is a definite range, so it's a finite Fourier sine transform. So the same thing goes for this is a finite cosine Fourier transform. So the inversion formula for function of x, or the inversion formula for sine Fourier transform, inversion formula goes like this: f of x is equal to 2 over pi summation n equal to 1 to infinity of sine, okay, this is okay, for your fx, we find this in this, so this is f of x of n, this is the Fourier of n, this is Fourier of fx, and the same thing also apply, this is f of n, not f of x. So that's that. So we have f of x equals 2 over pi summation comes starting from n equal to 1 to infinity of f of x of n sine nx. Sorry, there's no dx, so it's just sine nx. So this is a lot like the inverse Fourier transform for f of n. This is just like the inverse Fourier transform for f of n. So all this formula are going to be needed while solving our partial differential equation. So this is just like the inverse inverse Fourier transform for a particular sine function. So this is denoted as this. So the inversion formula for your cosine, Fourier transform goes like this: f of x is equal to 1 over pi of Fourier cosine transform of a particular function of, that's f of n, but in this case n is 0, right? So plus 2 over pi summation start from n equal to 1 to infinity of Fourier cosine transform of f of n cos nx. So this is the inversion formula for your cosine transform. So mostly we can actually use, more easier to use Fourier sine transform to solve to solve PDEs, because Fourier sine transform formulas are much easier and much are much more easier to use while solving PDEs. So now let's look at this example on how to solve this particular question on PDE using Fourier sine transform. So we are going to be looking at how to solve this partial differential equation using finite sine transform. So I told you that finite sine transform, it's finite because it goes from a limited range. Now we are given the limited range here, which is from 0 to pi, right? So now this is a finite range. So now that's why it's called finite sine transform. And I give you the formula to be integral coming from 0 to L. And in this case, L is equal to pi. So it's going to be integral coming from 0 to pi of fx sine nx dx. So it's denoted as finite sine transform of n. So this is how it's denoted as. So we are going to be using this formula to solve the PDE given in front of us. Now the first step on how to solve this equation is to multiply through by the sine transform itself. So we're having of course, now since our dependent variable is y, right? Our dependent variable is y. So our sine transform will be having alphabet y instead of f. So we'll just change it to y instead of f. So this is the finite sine transform of f of n. where y is the dependent variable, right? So now we're going to, since our dependent variable is y, we just change it to y. So now, since the equation given in front of us is dy, and y is a function of x and t, so no need to write it, so we just write dy dt, right, is equal to d square y divided by dx square. So now, we multiply through by the transform itself, or just not technically multiplying through, yeah, we multiply through by the transform itself. So this is what we have. So we'll now have dy dt integral, remember, y here is going to be a function of x and t, right? Y is a function of x. So we're writing the formula for sine transform we're using now. We'll be having y of Sn, or just y of n, integral come from 0 to pi y, which is a function of x and t, sine nx dx, right? So this is the sine transform formula we'll be making use of, right? So technically, we want to use this formula now to solve this PDE, right? So how do we use that to solve this PDE? So we're going to apply this formula to this place. Now, since we're already having y, which is a function of x and t here, what we just need to complete to give our finite sine transform on this side is just sine nx dx and my integral. Since I'm having y, which is this, what I need to complete this other side of the equation is sine nx dx and my integral. So I just add my integral, which is coming from 0 to pi sine nx dx. So same thing also applied to the right hand side. This is d square y over dx square, right? Remember, this is my sine transform I'm working with. So I already have my y, which is a function of x and t here. So to complete my sine transform, I just need to add my integral coming from 0 to pi of sine nx dx. So now it's complete. So I can just rearrange this as, so this dy dt integral comes from 0 to pi of y. Let's just put the sine, it's function of x and t there. So sine of x dx, right? I brought this into the integral. So the same thing also applies here. So in this case now, I can just rearrange it. So this is integral from 0 to pi of d square y dx square, y which is a function of x and t. So I can't split y out of this because it's having this is the second order PDE. So this is sine of nx dx. So now this is the first step. First step, I tend to express the PDE as the sine transform I'm given. So this is sine transform I'm having integral and y, which is a function of x and t, and sine nx. So since I'm already having y here, I just need to complete it with my integral coming from 0 to pi and my sine of nx dx. Same thing to apply it to the right hand side. This is what I have. So I just rearrange this, bringing this into the integral and bringing my y into the integral. So this is what I have. So this is my first step. So my second step, so first, bear in mind that y, the Fourier transform of y, is equal to integral from 0 to pi sine of y, which is a function of x and t, sine nx dx. So this is the finite sine transform I'm using to solve the PDE. Now remember, I just replaced the f on the usual formula we know. I just replace the f with the y. So this is the formula we are working with. So even when they asked solve the PDE using finite cosine transform, or you just replace the f with the dependent variable given and use the same formula. So now our second step, so we take the right hand side which is given as integral from 0 to pi d square y is a function of x and t over dx square, right? Sine nx dx. So we're going to use integration by part to solve this. So in this case now, the v will take the derivative, right? Because it's easier to integrate this derivative. And my u will take the sine nx. So the v will take the derivative, which is d square y. It's a function of x and t over dx square, right? So this is the right hand side of the equation. So we just take the right hand side of the equation. So integrating this now, integrating the v, so v will be left with just this dy dx, right? When I integrate a second order derivative, I'll just be left with first order. So differentiating my u now, so this will be du equals cos n cos nx, right? When I differentiate u, the n, this is a function, this is sine nx, so n will multiply the function I'm differentiating, then differentiating sine, I have cos. So applying to my integration by parts formula, which is u dv is equal to uv minus integral v du. So when my u is n cos nx, sorry, my u is sine nx and my v is dy dx. So this will be sine nx times dy dx minus integral my v, which is dy dx, times my du, which is n cos nx dx. Right, my du, when I differentiate with respect to x, so I'll be left with dx here. So that's just what it is. So in this case now, I'm having a second order, I'm still having first order derivative here. So I'm going to integrate this again. So taking this one out, so this is integral coming from, this is integral dy dx of cos nx, right? So the n here, I took it to the back of the integral sign, so I'm just left with dy dx cos nx. So let me just put it here, right? So I took this part, so I'm just integrating it again. So taking this part to integrate it, so when my u now my u will be cos nx, and my dv will be dy dx. So I'm just going to repeat the same process. So now I call this my third step, sorry. So I took this part to integrate it again. So differentiating my u, so this will be du dx is equal to minus n sine nx, right? So this is differentiating cos, I have sine, right? And multiplying the function as a function of, so just multiplying it by the function as minus sine. Remember, differentiating cos, I have minus sine. So integrating my dv, so this will be v equals y, right? Integrating dy dx, I'll just be left with y, which is also a function of x and t, right? So using my integration by part formula, this will be u dv equals uv minus integral v du. So my u, which is cos nx, right? So this is cos nx times my v, which is y, which is a function of x and t, minus integral my v, which is y, which is a function of x and t, times my du, which is minus n sine nx dx. So all this was from when I integrated dy dx cos nx dx. So I'm just going to substitute back into our main formula. This is our main formula. So I'm just going to substitute back. Remember, all I did was integrating this one. So I substitute this formula back into this. Then we continue solving. So we substitute this. So we substitute this into our main equation, right? This is our main equation. So substituting this into our main equation, so we'll be having sine nx dy dx minus, so there's an n here, right? So this is the integral coming from, this is integral dy dx cos nx, right? And this is what we had when we integrated it. So we stopped here because we had y. So we can easily relate it to something. So we can easily relate it to the sine with the Fourier sine transform of y with respect to n, right? So let's say with respect to n and t, or with respect to n. So substituting it here now, we'll have that. So first, let's substitute this into what we integrated as. So we left with n open bracket cos nx y is a function of x and t minus integral coming from y, which is a function of x and t, times minus n sine nx dx. So minus times minus is plus, so we'll be having sine nx dy dx minus, so n multiplying this, so this is n cos nx yx, which is a function of x and t, and minus, since minus times minus is plus, so we'll just be left with minus here. So minus integral coming from integral y x, which is a function of x and t, times n sine nx dx. So n, since there's n here, n multiplies this and n also multiplies this, so we have n here. So bringing n out to the back of the integral sign, so we'll be left with sine nx dy dx minus n cos nx y, which is a function of x and t, and this is minus n square integral y, which is a function of x and t, sine nx dx. So remember that our limit goes from 0 to pi. So this is from 0 to pi. Right. So now, before the starting of the video, we assume that y is a function of n. That's the Fourier sine transform of n is equal to integral coming from 0 to L. We said we are using the finite sine transform. At least that was the question said. So finite sine transform where L is equal to n, where L is equal to pi. So of function of x sine nx dx. Right. So we assume this, right? So we're going to substitute this or replace this with this right here. So replacing this with this. Remember, since we're having y, which is a function of x and t. Sorry, this is y, which is a function of x and t, right? And this, my Fourier sine transform to also be a function of x and t. So writing this, so this is Fourier sine transform, which is a function of x and t, will be equal to integral from 0 to pi, y, which is a function of x and t, sine nx. So we can substitute this now for this. So there goes my step 4. So step 4, I'm going to be substituting this now with this. So I'm left with sine nx dy dx minus n cos nx y, which is a function of x and t, minus n square integral. Well, since I can substitute this for this now, so I'm left with open brackets y, which is a function of n and t. Right. So remember this, this value here is what we had from our right hand side. So now let's bring in our left hand side. So remember our left hand side, well, I expressed it as d dt integral from 0 to pi, right, of y, which is a function of x and t, sine nx dx, right? This is what I expressed our left hand side to be. So these are right hand side, so equate this to be sine nx dy dx minus n cos nx y, is a function of x and t, minus n square y subscript n t. So now remember, when we integrated, our limit goes from 0 to pi. So don't forget to add the limit. So the limit goes from 0 to pi, 0 to pi. Right. So going from 0 to pi for my sine of nx dy. So when I substitute pi here, so this is sine pi, sine of n pi. So sine of pi is 180. So sine of 180 is always 0. So that will cancel out. So technically this cancels out. So when you substitute for pi and 0, it cancels out. So but for this one now, so this is minus n cos nx of y, which is a function of x and t, right? So substituting pi here, so I'll be left with cos n pi, right? But substituting pi here, this is y, which is a function of pi and t. So let's write it out. So let me just write this out. So this is cos, this is going from 0 to pi. This is n square y of subscript n t. So now if you remember our the condition we're given, so the boundary condition we're given goes like, so the boundary condition we're given that y, if x is 0, is equal to 0, and if x is pi, is also equal to 0. So this means that if x is 0, y, which is a function of x and t, will be 0, and if x is pi, it's also 0. So now if you look at where we are now, so we'll be substituting for pi and 0 as a value of x. So substituting it here, we'll be having minus n cos n pi y, which is a function of pi and t, right? Minus, open brackets, minus cos n times 0 is a function of t, minus n square y subscript n and t. So you see that it's based on our boundary condition. So based on our boundary condition, let's call this step 5. So based on our boundary condition, this here is 0. That is y is a function of y when x is equal to pi, y is 0, and when x is equal to 0, y is also 0. So based on our boundary condition, this is 0 and this is also 0. So we are left with minus n squared, your finite sine transform, which is function of n and t, right? So bringing our left hand side, so this is dy, this is d dt. It's going to come from 0 to pi of y, which is a function of x and t sine nx dx. So now I can also express this to, we said this is equal to this, right? So I can also express this one as my finite sine transform, which is d dt of y subscript x, which is a function of n and t, equals minus n squared y, which is a function of subscript n, is a function of n and t. So now this is so now what I did here, I just expressed this as my sine transform and apply my boundary condition. It cancels out my limit. So in order to solve this, if you look at this, this is a first order differential equation. So now, in order to solve this, we can easily solve this by separation of variable. Because if you see here, this is my independent variable, that's this dt, and this is my independent variable here also. So let me just rewrite this. So this is dy, which is a function of n and t divided by dt, equals minus n squared y subscript x, function of n and t. So I can solve this using separation of variable, meaning I'm taking my dependent variable to meet its derivative and taking the dt to the other side. So I can write this as dy, which is a function of n and t, divided by y subscript x, which is a function of n and t, right, equals minus n squared dt. So what's left for me now is to integrate both sides. So I call this my step 7. So integrating both sides, right? So integrating both sides and integrating both sides. So integrating both sides, right? So now this is dy, which is a function of n and t, divided by y, which is a function of n and t. So let me just rearrange this one. So this is integral 1 over y, which is a function of n and t, dy, right? Which is equal to integral from integral minus n squared dt. So if I integrate 1 over y, just technically if I integrate 1 over y, I'm just going to be left with natural logarithm, that's ln y, right? So this is ln y, which is a function of n and t, right? So equals, since I'm integrating with respect to t, right? So integrating dt, so I can just write this as minus n squared integral dt, right? So integrating dt only, so this is minus n squared t plus a constant k. So this is integral, this is ln y subscript n of n and t. So instead of me writing n and t, let me just write it as y. So this is ln y, right, equals minus n squared t plus k. So since this is a constant, I can just express it in terms of another constant, because since we don't know the value, we can express it in terms of another constant. So I can express k as ln a, right, for uniformity. So taking ln a to the other side, so this is ln y minus k equals minus n squared t. So since I express k to be ln a, so this is ln y minus ln a equals minus n squared t. So applying the rule of logarithm, so you know that log or ln of a minus ln of b is equal to ln a over b. So I'm going to apply it here. So let's call this step 8. So I'm going to apply it here. So this is ln y over a, right, equals minus n squared t. So we know that ln is natural logarithm to the base e. So this is log to the base e of y over a equals minus n squared t. So taking the exponential based on rule of logarithm, log to the base a of a, which is when is equal to b, can be written as a over b equals a. So I'm going to apply it here also. So this is let's call this step 9. So this is y over a equals exponential minus n squared t. So I applied this rule here to this. So I can multiply or cross multiply both sides. So step 9. So I'll be left with y is equal to a exponential minus n squared t. And do not forget, my y was my Fourier sine transform of n with respect to t. So it's equal to a exponential minus x squared t. So let's call this equation 1. So now this is what we had when we integrated. This is what we had from our. So this is what we had when we solved using separation of variable. So now step 11 goes like this. So we bring in our initial condition, right? So we know that my initial condition from the question was giving us. So my initial condition from the question was giving us when t is equal to 0. This means that when t is equal to 0, y is equal to x squared, right? So I can write it as when t is equal to 0, y is a function of x and t is equal to 0. So that's what the initial condition is saying. So we apply my initial condition after solving using separation of variable. So applying my initial condition, which says this is when x comma 0 is equal to x squared, right? But first, you remember that my sine transform of n and t is equal to integral from 0 to pi of y, which is a function of x and t sine nx dx, right? Remember this formula, right? This is our finite sine transform. So and since this is equal to this and this is also equal to this, right? So let's say when t is 0, right? When t is 0, we'll be left with y n comma 0 is equal to integral from 0 to pi of y x comma 0 sine nx dx, right? This is when t is equal to 0. So I just substituted t is equal to 0 into the general form we are having. So I'm left with integral from 0 to pi. Now we said when we're having t is equal to 0 for my y, which is a function of x and t, is equal to x squared. So substitute this now as this, right? So this is x squared sine nx dx. So this is y n comma 0, right? So we are still going to come back to this equation, right? So now we're going to solve this using integration by part also. So this is when u is equal to x squared and when dv is equal to sine nx, right? So differentiating my u, so this is du equals 2x dx, right? And integrating dv, this is v is equal to minus cos of nx divided by n. So I'm going to substitute these values or these parameters into the integration by part formula. So substituting these now into the integration by part formula, which says uv minus integral v du, right? So my u now is x squared times my v, which is minus cos nx over n, right? Then minus integral my v, which is minus cos nx over n, times my du, which is 2x dx. So let me just rearranging this now. So this is minus x squared cos nx over n plus integral cos nx over n times 2x. So since 2 and n are both constants, so take it to the back of the integral sign. So this is 2 over n integral x cos nx dx. So this is minus x squared cos nx over. So it's good using applying integration by parts, right? So because this is x and this is cos nx, we're having two functions of x, so apply integration by parts. So my u is equal to x and my dv is equal to cos nx. So differentiating my u, so u is equal to, if I differentiate u, which u is equal to x, so differentiating u, I'll be left with just 1. So that's du is equal to dx. So integrating my dv, my v will be sine nx over n, right? So substituting back into the integration by part formula, so this will be left with, so we're having uv minus integral v du. So uv, which is u, which is x, so x times v, and v, which is sine nx over n, right? Minus integral my v, which is sine nx over n, times my du, which is cos nx. my d, which is just dx. So n is a constant, take it to the back of the integral sign, so we're left with x sine nx over n. So since this is n, so taking 1 over n to the back of the integral sign, so this 1 over n integral sine nx dx. So I can integrate sine nx, so we're left with x sine nx over n minus 1 over n times minus cos nx over n, because when I integrate sine nx, I'm left with minus cos nx divided by n. So this can multiply through, so we're left with minus x sine nx over n plus cos nx over n squared. So this was what we got from integrating this, right? So I'm going to be substituting this back to that equation. So our general equation will be written as minus x squared cos nx over n plus 2 over n, open bracket, minus x sine nx over n plus cos nx over n squared. So multiplying through by 2 over n, so we left with minus x squared cos nx over n plus minus 2x sine nx over n squared plus 2 cos nx over n over 3, right? Because 2 over n multiplying this, that's what we have. So don't forget your limit going from 0 to pi, applying the limit coming from 0 to pi. So putting my limit here now, when I put pi, when I put pi here, so substituting x when x is equal to pi, so I can write the equation as minus pi squared cos n pi over n. Putting pi here, so since this is a sine function, and when the sine of pi of even irrespective of the value of n here is going to be 0, so I'm left with plus cos plus 2, that's 2 cos n pi over n raised to power 3, right? So minus, substituting when s is equal to 0. So putting when s is equal to 0 here, if I put s is equal to 0 here, this becomes 0, so all this becomes 0. So the same thing that goes for here, all this becomes 0. So I'm left with just this, right? This is 2 cos n times 0, right? Because this is nx, so n times 0, and cos 0 is 1, so I'm left with 2 over n raised to power 3. So you can write the equation as minus pi squared cos n pi over n plus 2 cos n pi over n raised to power 3 minus 2 over n raised to power 3. So this is what we got when we integrated x squared sine nx dx, right? So coming from 0 to pi. So this is what we had. And remember, this was equal to Fourier sine transform of respect to n and t, which was equal to integral from 0 to pi of x squared sine nx dx. So we can say this is equal to this, right? So this is minus pi squared cos n pi over n plus 2 cos n pi over n raised to power 3 minus 2 over n raised to power 3. So let's call this, so this was when it's equal to 0, right? So this was when t is equal to 0 that we had this, right? So we integrated this and we had this. So let's call this equation 2. So this was my equation 1 and this was my equation 2, right? So I'm just going to be comparing equation 1 and equation 2 together. So so now this was my equation 1 and my equation 1. So so my equation 2 says when t is equal to 0, right? So now in order to compare the two equations together, let's say t is equal to 0 for my equation 1. So I'll be having y with subscript x, comma 0 equals a. So when I put t is equal to 0 here, 0 times this is 0, and exponential 0 is 1. So I'm just going to be left with a, right? So comparing this equation and comparing this equation together, so my a will be equal to minus pi squared cos n pi over n plus 2 cos n pi over n raised to power 3 minus 2 over n raised to power 3. So this is the value for my constant a. So let me assume this is my general finite sine transform of this. That's my equation 1, right? My equation 1 is a function of n and t. So since I've gotten the value for my a, I substitute back into this equation 1. So y subscript x, n and t is equal to minus pi square cos n pi over n plus 2 cos n pi over n raised to power 3 minus 2 over n raised to power 3 multiplying exponential minus n squared t. So this is the finite, this is the formula, this is the value of my finite sine transform. So now we're already done with our solution, so let's introduce our inversion formula. So I said the inversion formula is what we use to round up the solution. So I don't know what step we are, so let me just call this my last step. So I don't know what step we are, so I just call it my last step. So my last step now is to introduce the inversion formula. So when I've gotten the value for my finite sine transform of the function, so I can introduce my inversion formula. Right. So the inversion formula, remember I gave you the inversion formula for a function of x. I said the inversion formula for a function of x is function of x equals summation, that's 2 over pi summation n equals to, from n equals to 1 to infinity of sine of Fourier sine of n sine nx, right? This is the inversion formula I gave. So in this case now our dependent variable is y, not f. So we just change it as, and my dependent variable is the function of x and t, not just function of x. So we'll be having y is a function of x and t will be equal to 2 over pi summation n equal to 1 to infinity of sine transform. And since the Fourier sine transform is a function of x and t, so when x goes to n, I'm left with just n is a function of n and t. So left with function of n and t sine nx. So this is inversion formula. So since we have gotten, so I said this dependent variable is a function of y, not f. So we just change it to y. Now for uniformity. So since I've gotten the value for my finite sine transform, so substitute it back here to get the solution to the get the solution to the PDE. So I'm left with y is a function of x and t is equal to 2 over pi summation n equal to 1 to infinity. Substituting this to this, so we left with we having minus pi square cos n pi over n plus 2 cos n pi over n raised to power 3 minus 2 over n raised to power 3, right? Exponential minus n squared t, then multiplying sine nx. So this is the solution to that PDE. After we've gotten the value for the Fourier sine transform, what we did was introducing the inversion formula in order to get the solution for y is a function of x and t. So basically, for heat equation and for wave equation, we just need to get the what we just involve was getting the value of x and t. So it can be, so your equation can come in terms of u, or mostly comes in terms of u, but this question came in terms of y. So it's still the same process in solving all of that. So thank you for watching, and please do so well to subscribe.